Let's have a look at maximum earth fault loop impedance values and why we get different values in BS7671 and in the on-site guide. So here's the tables for ZS from the two publications. We're just going to concentrate on Type B circuit breakers to 60898 and 61009, they're your RCBOs. And for the 20 amp RCBO in 7671, the maximum earth fault loop impedance is 2.19. Then we got the on-site guide. We look at the 20 amp Type B RCBO, and this time we get a value of 1.75. Now these are both maximum values. So how can you have two different maximum values? So here I've got the full table for 7671 and the on-site guide with all the various different size protected devices. So this column's your IN. That's a rated current of your protected device. Then we've got the two values for earth fault loop impedance. Let's quickly go through what earth fault loop impedance is. I've got a video on this, but we'll just have a quick look. So in this drawing I'm going to ignore the neutral. We've got three sections. We've got the external section, that is known as your ZE. We've got the distribution board with the protective device. Then we've got the final circuit, that's known as your R1 plus R2. The two things combined are your ZS. We'll follow the flow of power from the transformer in the street. Power comes from the transformer through any service fuse. It'll go through your protective device and onto the final circuit where it'll power a load. The neutral will complete the return path back to the transformer, so you've got a complete circuit. We also have a protective path back to the transformer. This is our circuit protective conductor, and it will clear any faults. If you do have a fault, the fault will follow that path. So you have a short between line and earth. The fault current will go down the CPC, through the main earthing terminal, back to the transformer in the street, back through the service fuse, into the protective device, and operate the protected device, switching off the circuit, removing any danger. That is your earth fault loop impedance path. We want to clear this fault as quickly as possible, and is timed in BS7671 for how quickly this circuit has to disconnect. Generally it's 0.4 of a second, but there's different times. We'll stick with 0.4 for now. So we want this protected device to trip within 0.4 of a second. The greater the fault current, the quicker the protective device will operate. If the fault current is too low, the protective device won't operate at all. So what we need to do is make sure that enough current goes down this earth fault loop path to trip the device in the correct time. If you've got higher resistance, we're going to have less current. So our earth fault loop impedance is making sure that the resistance of our cables will not limit any fault current. Actually, it's not resistance, it's impedance. We're not going to get too much into this, but it is important. Resistance is simply defined as the opposition to flow of electric current in a circuit. Impedance is the opposition to flow of AC current in a circuit, because loads can be resistive, inductive or capacitive, and this can affect the flow of current. So just to make sure we've got this, it's a fundamental principle in our protection against electric shock, automatic disconnection of the supply. We want a low resistance and a high fault current to guarantee ADS. This is to protect us. The longer a fault exists, the longer somebody could be receiving an electric shock. So we want to cut it off as quick as possible. And because MCBs have tripping characteristics, they need a certain current to operate instantaneously or within 0.4 of a second. And if you start getting a high resistance and a lower fault current, the MCB might trip at some point if there's enough current, but how long it takes, nobody's going to know. We can't have a system that protects us on if possibly or might. So we've got to make sure this device will operate within 0.4 of a second. If we don't have that high fault current and low resistive path, ADS is not achieved, and obviously it's an increased danger. So back to our two tables. I'm going to stick with resistance for now. So we have to trip this protected device within 0.4 of a second, say. And depending on the IN, the rated current of the protected device, we get different values. If I had a 6 amp circuit looking at BS7671, the maximum resistance of that circuit, so that RCBO would trip within 0.4 of a second, is 7.28 ohms. The on-site guide tells me it's 5.87 ohms. If I had a 32 amp protected device, 7671 says 1.37, on-site guide says 1.1. So that's the maximum resistance that this circuit can have. So that protected device will operate in the required time. So if we know the maximum earth fault loop impedance, we can work out the maximum length of the circuit. This is useful when you're calculating. Don't forget the maximum earth fault loop impedance will also include the ZE. We might not know what the ZE is, but we can use the maximums, and often it's going to be a lot less than the maximum. So for TNCS, ZE of 0.35. So for a 6 amp circuit, it's going to be a lighting circuit, 1.5 1mm squared cable, R1 plus R2 of 30.20 milliohms per meter. For calculation purposes, you can do this. You wouldn't do this when you're measuring. We can minus the ZE, 0.35, from the ZS, 7.28, gives us 6.93. So we divide that by 30.20 times 10 to the minus 3, and that gives us a maximum length of 229 meters. Times 10 to the minus 3 is like dividing by 1,000. That's the values of BS7671. Interesting thing, if you look at the on-site guide and use their values, it will give you a maximum length of 182 meters. And the reason for the difference is temperature. We're going to get onto this shortly. And don't forget, these are the maximum values. You don't really want to be installing a circuit which is 229 meters in length, do you? Especially in domestic. And this is just a very basic first calculation. You will have other correction factors which will affect the length of the circuit. We don't have to take everything to the limit, but we have boundaries in which to work. There's not much we can do though until we know the design current and the rating of the protected device. So let's have a look at this 20 amp RCBO. 7671 tells us the maximum earth fault loop impedance is 2.19 ohms. Now, where did they get that 2.19 from? Let's have a look. Okay, so we're looking at table 41.3, type B circuit breakers. We want a 20 amp. That type B can be a bit confusing. It's recommended to be installed type A RCDs. Now these are two different things. The B curve, the B20, this thing here, that's your IN, the rated current of the protected device, is a B curve. And that's the operating characteristics, that it takes 5 times the rated current to trip the device instantaneously. Type A tells you what kind of loads it can deal with. We'll be used to the AC type RCDs, which we're starting to get rid of now, and we're installing type A RCDs, which can detect AC current and pulsating DC current. We also get type F and type B. So we've got a B curve type A RCD here. Just quickly, what are the other things? We have a schematic. This generally tells you how it's switched, how many poles. Does it just switch live or does it switch live and neutral? Tell you the voltage, the frequency, the short circuit breaking capacity, how much fault current it can handle, the rated residual operating current. But when we're doing our ZS, we're interested in its operating characteristic, the B20. So we're looking how they get to the value of 2.19 ohms for our maximum earth fault loop impedance for this 20 amp RCBO. This is the formula. ZS equals UO times C min divided by IA. UO, that's your voltage to earth, 230 volts. C min is a correction factor for voltage fluctuations, and that's 0.95. And IA, that's the operating current of the protective device. Remember we talked about the type B? Type B is 5 times the rated current. So 230 times 0.95 is 218.5, and we divide 218.5 by 100, our fault current, and it gives us 2.185 ohms. And I've rounded that up to 2.19 ohms, maximum earth fault loop impedance for a 20 amp RCBO. That's how they calculate these numbers in BS7671. Now, why do we have different temperature values between BS7671 and the on-site guide, for example? BS7671, the conductors are at their maximum operating temperature of 70 degrees C. The on-site guide is at an ambient temperature, which they've decided is 10 degrees C. And because resistance increases with temperature, we get different values. The higher the temperature, the greater the resistance. So we need to take into account the temperature when we're calculating our earth fault loop impedance or we're measuring our earth fault loop impedance. When we're calculating, we want to consider conductors operating at their maximum limits. So we'll be using BS7671. When we're on site actually testing an installation, we'll be doing at ambient temperature. We might use the values that are calculated in the on-site guide. And if we're doing a measured test, we have to make sure that our measured test would not exceed the values of BS7671. We also need to adjust our values for conductor resistance when we're doing our R1s plus R2s. We'll go through all this. So the reason for the different temperatures becomes clear when we realise that we have to work within certain boundaries. Our conductors have maximum operating temperatures. For thermoplastic, that's 70 degrees C, and for thermosetting, that's 90 degrees C. If you look through the tables at BS7671, thermosetting insulated cables have a greater current carrying capacity than thermoplastic. An example being 4mm SWA, thermoplastic clip direct has a current carrying capacity of 38 amps, where thermosetting 4mm clip direct has a current carrying capacity of 49 amps. So you'd think, it's better to use thermoset all the time. The insulation is suitable for up to 90 degrees. You're going to get better values when you're doing your cable calculations. But then we have regulations 512.1.5, which causes a bit of a problem with that. Switchgear, protected devices, accessories and other types of equipment shall not be connected to conductors intended to operate at temperatures exceeding 70 degrees C at the equipment in normal service, unless the equipment manufacturers have confirmed that the equipment is suitable for use in such conditions. The regs do go on to say we can use 90 degree cable, but only if we do our calculations to 70 degrees C. Our MCBs, our switches, our sockets, they're all rated for 70 degrees, not 90. When we're doing our cable calculations, we want to be thinking about the conductors at their maximum operating temperature. So we'll be working in this range. When we're measuring or testing an actual installation, we'll be doing that at ambient temperature, whatever that may be. So we'll be working in this type of range. But we need to be able to verify our readings in calculations against each other. We need to know that our ambient test will still be compliant at the maximum operating temperature. When it comes to temperature, things can get very complicated very quickly. Thankfully, it's not too difficult. It's just a bit of simple sums, really. It's simple math, but I'm still capable of looking it all up. You will notice some little oddities with the numbers. Our coefficient formula, 1 divided by 1.24 is 0.806. To get 80%, it's actually 1 divided by 1.25. I don't think we need to be too concerned about the second and third decimal place. I mean, we're talking really small resistances here. 0.01 of an ohm is about half a metre, 2.5 to an earth. So I don't think we have to worry about that. You're going to see a bit of rounding up. You can make it as complicated as you want to make it, but what we're looking for really is the 80% values. And we have various factors which we either divide or times by, so we can compare our values at different temperatures. We have a different ambient temperature, we have a correction factor we can times by. The on-site guide and such have a formula for the temperature coefficient of copper at 20 degrees C. It's a simplified formula. So for example, BS7671 and the on-site guide, their maximum earth fault loop impedance tables, have a temperature difference of 60 degrees C. So that in our simplified formula would be 1 plus 0.004 times 60 for the temperature difference, and that equals 1.24. And that is the factor that we use when we're doing our calculations. It's had various names over the years. It used to be the rule of thumb, just a very basic calculation. The highest measured ZS value for each of the circuits should not exceed 0.8 of the relevant value in the tables in BS7671. So you can see how they got the 80% and 0.8. 0.8 is 80%. 1 divided by 1.24 equals 0.80. So for the 20 amp type B MCB, BS7671 tells us 2.19 ohms. It's a maximum earth fault loop impedance. If we wanted to know what that was at 10 degrees from the on-site guide, we need to adjust the temperature by 60 degrees. We'll times 2.19 by 0.80, and that'll give us 1.75. And as you can see, the value in the on-site guide, the maximum earth fault loop impedance at 10 degrees is 1.75. Down the side here, I've got the correction factors for the increase in temperature. Say for example, we had 1.75 ohms, and that was tested at 30 degrees. We times that by 1.08, it'll give us 1.89 ohms, and that would be our maximum ZS at 30 degrees. You see it's gone up a little bit. The higher the temperature, the higher the resistance. So basically, BS7671 is the 100% values, and things like the on-site guide are the 80% values. So when we come to do our measured test, in this example here, plugged in our tester, we've got 0.52 ohms. We need to make sure that that 0.52 ohms doesn't exceed 0.8 of the relevant value in BS7671. The on-site guide have done the work for us. They've got the 80% values. 0.52 is obviously less than 1.1 ohms, so we know that the circuit's got to be compliant. But if we didn't have the on-site guide, we just had BS7671, we'd times the value 1.37 ohms by 0.8, and it'll give us our value, 1.09 ohms. Our 0.52 ohms is less than that, so we know we're compliant. And you can see here, our 0.52, if we corrected that up to 70 degrees C, it's 0.64 ohms. So we're still well under 1.37. We're always going to be under the maximum ZS if we're under 80% of the maximum. When complying with the regulations, maximum ZS and automatic disconnection of supply will be achieved. In this example, we've took another measurement. This time we got 1.29 ohms. If we look at the maximum in BS7671, we're under 1.37 ohms, but we're not compliant because of this temperature difference. Then we've got 80%, it's 1.10 ohms. We've got 1.29. And you can see, if we calculate up from 1.29 to 70 degrees C, we have a reading of 1.59 ohms. And we're above the maximum in BS7671. So you can see how the increase in temperature made the circuit non-compliant, and ADS is not guaranteed. There are other formulas and there are other ways of doing this. So let's have a look at a few more. So here's the formula we use for calculating maximum ZS. We've got the temperature correction of 0.8, and we're comparing our measured value against this temperature corrected value. And if our measured reading is less than the corrected reading, we know that we're compliant. And the protective device should operate in the correct time. Let's have a look at the maths for this. So imagine doing a live ZS test on a socket. So we plug in our tester, we get a ZS reading of 0.52 ohms. And this is how we worked out the maximum ZS reading, remember? 230 times 0.95 divided by 100 gives us 2.185, which we rounded up to 2.19 ohms. Now with this correction factor, 0.8 times 230 times 0.95 divided by 100 is 1.748 ohms. The impedance of this earth fault loop path will be less because it's at a lower temperature. We compare our measured reading of 0.52 against our temperature corrected maximum reading of 1.748. So our ZS measured is less than the corrected value of 1.748 ohms. So we know that this circuit is compliant with the regulations. So we know how the calculation works for the maximum earth fault loop impedance. And we also know that we can correct that value for the ambient temperature that we're testing at. We also need to consider the ambient temperature when we're measuring or calculating our R1 plus R2s. So our ZS formula is ZE plus R1 plus R2. And as we recall, the ZS is made up from our ZE, the external impedance, and our R1 plus R2, the internal impedance or resistance. For the purpose of this example, we're just going to use the maximum ZE allowed for a TNCS system, which is 0.35 ohms. TNS, it's 0.8, but since everything is practically TNCS now, we'll stick with 0.35. When we actually test the ZE at the installation, you're more than likely to get a lot lower number than that. So when you're calculating your maximum ZS, you're going to want temperature corrected values of R1 plus R2. You might be verifying a circuit, so you just want to do that at ambient temperature. Let's have a quick look at how to get the R1 plus R2 at 20 degrees. Now the R1 plus R2, the R1 is our line conductor, the R2 is our CPC. And when we're calculating this, we can get values for R1 plus R2 in the on-site guide and various other publications, and they will give you the milliohms per meter for the various conductors. In this example, we've got a B20 RCBO. It'll be feeding this socket circuit with 2.5mm squared twin and earth cable. And the length of the run is 30 meters, twin and earth. It's got a 2.5mm squared line conductor and a 1.5mm squared CPC. So we can work out the milliohms per meter value of those conductors for the length. So if you've installed or you're testing a known length of cable, you can work out what the expected resistance is. You can compare your measured reading against the tables in BS7671 at 20 degrees, and you can see if you're getting the right resistance. This is the formula we use when we're calculating our R1s and R2s. Milliohms per meter times length divided by 1000. We get the milliohms per meter reading from our tables. We times that by the length, which was 30 meters. We divide by 1000 to get the value from milliohms to ohms. We can do it individually. We could calculate the 1.5, which is 12.10 milliohms per meter. So we times 12.10 by 30 and divide by 1000. And that would give us a value of 0.36 ohms for 30 meters of 1.5mm square cable. We could do the same for the 2.5 conductor. This time we'd use 7.41. 7.41 times 30 divided by 1000 will give you 0.22 ohms. That's our R1. To save time, you can combine the two. The on-site guide also gives us the combined R1 plus R2 milliohms per meter, which is 19.51. And as you can see, all they've done is they've added the value for 1.5 and 2.5 together, got 19.51. So we'll use this value to calculate our R1 plus R2. So 19.51 times 30 divided by 1000 gives us 0.58 ohms. So our R1 plus R2 is 0.58 ohms. Our ZE was 0.35, so we can add the two together. ZE plus R1 plus R2 will be 0.93 ohms. So our ZS, our calculated ZS, is 0.93 ohms. It's important to remember that this is a test at 20 degrees C. We're verifying an existing circuit. So we're verifying the resistance is correct for the ambient temperature. If we wanted to verify that these values would be acceptable at maximum operating temperature, we'd have to adjust the values, and then we could see if they're compliant at maximum operating temperature. We only correct our R1 plus R2s. We don't add any correction factors to ZE. We've got no control over ZE. We get given a value, which is usually the maximum, or we can take a reading. Right, here's a couple more examples. This is a formula here. ZE plus R1 plus R2 times CR times L has to be less than Z41. A few new terms in here. The R1 with the asterisks above it, that's our milliohms per meter value. CR is our correction factor, and Z41 is our maximum earth fault loop impedance values in BS7671. I've used these terms because these terms are often used in other guidance, in Guidance Note 3, and also Electrical Installation Design Guide. So there's two different types of cable here. The green, that's twin and earth cable, and the purpley one, that's SWA cable. R1 plus R2 readings. I've done the calculation at 20 degrees C, and I've also done the calculation at 70 degrees C. And so this is the circuit. We've got an EV charger, 7,000 watts. The design current IB is 30.43 amps. The rated current IN is 32 amp RCBO. This is not a cable calculation. We haven't done the correction factors on the cable and such. So 4mm twin and earth has a current carrying capacity, IZ, of 37 amps. It's got an R1 of 4.61 and an R2 of 12.10. The circuit length is 35 meters. We look at steel wired armour. That's got an IZ, current carrying capacity of 38 amps. Got an R1 of 4.61 and the R2 is 4.61 as well. In SWA, the CPC, the R2, is the same cross-sectional area as the R1, your line. You'll notice when we get to the final values, that having the same size cross-sectional area CPC as a line conductor will obviously give you a lower ZS value. So let's have a quick talk through it. So we've done our calculated ZS for the twin and earth circuit, 20 degrees C, we got 0.93 ohms. Same circuit at 70 degrees C, the resistance is increased to 1.05 ohms. The same with the SW earth, 20 degrees, 0.67 ohms. 70 degrees, 0.73. And again you can see with an increase in temperature, you get an increase in resistance. An increase in resistance, you're going to get a decrease in fault current. You've got to keep that resistance or impedance underneath the maximums. And these are the various tables in the on-site guide for the different correction factors. So I think that's it for this one. Well done for getting this far if you managed it. I hope it's been of some help. And as always, thanks for watching.